Hello everyone, so welcome back. This is your data mining class with business applications. So we are jumping from chapter 5, which is the cross validations chapter, to chapter 8, which today we are going to talk about the basic tree methods. So as most of you guys have seen, the tree models, it's a very common and basic models in statistics, how we classify it, or maybe to give estimations or predictions for some unknown variables. So today we would like to go over the our codes that we usually use to build a basic tree models. And today we are going to use the car seat dataset from the ISLR library to do the tree models. So here we would like to basically put in a remove functions here, just in case. This is a very good practice for students first time learning programming. Whenever you're working on several projects or several files at one single time, you might actually get confused about what it's being stored in your global environment. So it's always good when you're starting a new project or maybe a new set of codes, you want to first remove whatever that is stored in your global environment. So using the remove functions here, you basically clean up all the things previously stored in your global environment. So to demonstrate again, well, I can actually say, well, x is equal to 2. So, oops, sorry, the other way around. So it's equal to 2. So as you can see, I'm storing a variable here, right, in the global environment. If I want to remove it, I can actually use the remove functions here again. So as you can see, I'm removing that variable being stored. And today we're going to use the data sets from the ISLR library. So we're calling the data sets here. And we are going to use the tree models today. So I'm going to call it the tree libraries. If you have not installed this tree library before, please run this code right here, install.package tree. So I have already installed it, so I can just literally just call it out. And I'm going to basically use this CASIT dataset today to explain the tree models. So I'm going to attach it. Well, let's take a look at the car seat datasets. So as you can see, the car seat dataset actually has a few columns here. So if you want to know how many observations and columns the datasets has, you can use the dimensions functions, DIM. So there are a total of 400 rows and 11 columns. So that means there are 11 variables that you can use in this dataset. And if you want to actually print the summary of the dataset, you can use the summary functions here. If you want to just call out the summary of a particular variable, you can actually now put in just the column names right here within the summary functions. So for instance, you're seeing the columns here with shift locked. There are basically 3 different values here: good, bad, and mediums. You want to know how many goods, how many bad, how many mediums are in the data sets. You can basically just say summary, and it will print the total frequencies of each class in this categorical variables. And of course, you can also use the summary for the whole data sets like this. So it will also print the whole data summary here for all the variable. But just in case, if you are interested in just one particular columns of data, you can use the summary function for that particular column names, and R will detect it from the data. So today, our main objective is to try predicting the sales price for car seats, and we are going to use all the variables in our data set and put it into a tree model and train it. So now, before we're doing anything, we would like to split the data into a training set and a testing set. So we are going to randomly basically divide the data into two groups so that we can use the training set to train our model in the tree methods to train it, and we are going to basically use the testing data to test how well the model actually provide the predictions for an unseen testing data. So again, I'm setting a random seat right here. So I'm going to use random seats 1 right here for my observations. So you can set any number. Again, the random seats basically describe you a particular patterns, how you want to randomize your samples or randomize generations of numbers. You can actually set it to 2, 3, 4, but if you want to get the same result as my demonstration, you can keep this one right here. In the later time, if you want to play around with the data, you can actually set this to a different number, like random seats 2, random seat 3 or 4, and every number that you put into this random randomizations process, it will actually give you a different randomized numbers. So here we are going to first store this number of rows from this car seat data into a variable called number of observations. And we print this, and we can see there are 400 rows, so that's why the number here we have is 400. It's always a good idea to store some of this very important number into a variable so you can actually reuse it over and over again. So this is the part of programming that you should learn. When you're doing your job, you probably want to make your programming a little bit more dynamic than just hard coding everything. You don't want to check back the number of rows and later to put in 400 every time in your code. So instead, you want to create some variable to actually reuse it over and over again without putting the number into your code. So the split of the data here, we're going to split the data into half and half, 50 and 50. So we are putting in 0.5 as our split of a train test sets. And now what we want to do is use the sample functions here to randomize samplings from our data sets. So we are basically going to randomize samples and pick the samples from our existing data sets. So we want to have 1 to 400, which is the total number of rows put into our randomized process. And we would like to actually have 400, the number of observations, times 0.5, which is half of our observations. So we want to actually draw 200s out of the 400s here. So we call this a training here. So again, if you want to hard coding this, you can actually do this. So train equals to sample 1 to 400s, which is the index number of your data sets. And then you want to call out 200 random number out of 1 from 400s. And then I'm going to define whatever that it's not in the training index. So for example, if the training index from 1 to 400, you pick up, let's say, 2, 5, 6, 10, 11, those numbers will not be included when you specify minus signs here. So basically, we define whatever that it's already picked in a trainings index will not be included in a test index. So again, well, let's run this. And I'm going to run the test. Again, let me just comment this out so it's the same here. Now, what I want to do is to create a training data sets from our data sets car seats, and we only want the index number from our trainings here that we defined. So remember, we pick some number, random number from 1 to 400 randomly, and we are going to put it here to basically let our nodes which rows we want to actually extract from our original data sets. So once we extract those index number, the number of rows in our data sets, we are going to store this into a train data. And we also want to do the same thing for the testing data sets. We called the data sets, and we only want the number of rows in the test index. So once we create those two, the training sets and the testing sets, and now we can actually, this is our testing outcomes. So again, well, the test outcome basically refer to the cells, right? So the cells is the one that we care about here. So it's the response of our tests. So we're going to store that. We will use it later, not for training purpose, but later we're going to use it for a testing purpose. All right, so once we get here, we are going to start making a tree models. So to build a tree model, again, you will need to load the tree library. So again, the library tree should be loaded up for now. So all you need to do is basically using the tree functions. So you see there's a tree functions here. You're gonna put in the cells, and you are using all of your variables in the data sets. Again, the dots, hopefully you remember now, the dots basically refer to all. And you are going to use only the training data sets to train your models. And you're gonna save it to this tree model here. So let's run this. And I'm gonna try to remind you, this language right here, or the syntax right here, it's very, very extremely similar to our regression models and logistic models, also the LAD model that we have learned. So again, if you want to run the same thing by hand typing everything, you can also do something like this. So tree models equals to tree cells, which is the response variable, and then you start adding those different model, the variables in there. So for example, we have comp price, and then plus income, plus advertising, and plus so on, and then all you need to do is to define the training data, right, in your models. Again, well, very similar to your regression modeling, but since we're using all the variable here, so why not we just put the dot here. Let's print the summary. So again, the summary output does not give you a lot of things that it's interesting to evaluate. There is not much of a numbers that you will see from this model. You won't see any parameters of estimations like your regression model or logistic model. But instead, well, there are some very important information you should note about this output. First of all, the tree functions will allow you to model the data and trying to put it into a tree structure. However, as discussed in the the class lecture, you should know that not all the variables will be used to construct a tree. Only the most significant ones that minimize the mean square error will be used to basically create a tree leaves. So in this case, you can actually see we have 11 columns. So that means we have cells. Except for cells, we have 10 variables that we could possibly use to construct a tree model. And this summary outputs actually tells you we are only using 6 out of the 10. The shelf logs, price, age, advertising, comp price, and US. So those are the 6 variables that we actually use. The models, the tree models actually determines and trying to, as you can imagine, it's basically try to fit different variable into a tree and trying to figure out, well, how this tree model can minimize the mean square error for the training data sets as much as possible. So some of this variable might not be actually related to project or predict the cells, will not be used in the tree structure. So only 6 of them are being used. And also, as you can see, the tree model also determines how many number of terminal nodes is going to be used and created. So out of the 6 variables that we include in the tree structure, there are 16 terminal nodes it's being created to make a final predictions of the cells in the data sets. And also another very important things to note is the residual mean deviance. So the residual mean deviance reports basically the deviance of the models. It basically gives you an idea how well the models actually do. The distributions of residuals basically give you, again, another idea about how the residuals are being quantified. Right? So it minimizes at the number of negative 0.882 and maximize value here, and the mean values will always be zeros. Right? So the distributions of residuals should always have a mean equal to 0. So now we have a summary of this. Well, 2 very important informations you should note is, well, what's the variable used, what are the variable used in the tree structure, and how many terminal nodes. Well, one very good advantage about the tree model is you don't really need to look at those numbers specifically. Instead, what you want to do is to visualize it with a tree structure. So you can actually simply plot the tree models by using the function plot in R. So again, since the tree model is going to look a little bit big, so let me just enlarge the printing window here. So let's plot the tree model that you just created. So as you can see, there is a tree structure here, but when you are using a plot functions for a tree model, unfortunately, it won't give you the text of the name of the variables, how it's being split out in this tree model yet. In order to print the text on your tree model, you have to use this text functions right here. So you use the text functions, you call out the tree models, and then you want to use pretty equal 0 when you have a categorical variables included in your data sets or as one of your features. So again, when your features or predictors has a categorical variables in there, you have to use pretty equal 0 in order to identify that categorical variable. If all of your predictors or features are basically quantitative, it's not categorical, but it's actually numerical, then you can ignore not using the pretty equals 0 parameters. So let's take a look of what we use. So we use shelf lock, price, age, advertising, comp price, and US. So I believe US and shelf locked is basically the categorical variables in our data sets. So that means I must include the pretty equals 0 parameter here. So let's run this. Well, it's pretty dense. Unfortunately, the out programs itself does not have a very pretty tree diagrams printouts. You can actually use different libraries out there to print your tree outputs into a better format. But well, in general, what we want to know is how the tree is being structured here. So as you can see, I have the models here that initially being split up by this shelf locked. So that means I have all the data sets, the training data sets that I have in the data set, and I am splitting the cells columns into two parts. One goes to the left, the other part goes to the right. Well, this category here in the tree models specified basically tell us the bad and the medium class. It's being split into onto the left hand side of the tree. Well, obviously the leftover, the goods category or the good class basically split to the right hand side. Well, going down to the right hand side, well, for the good category, for shell locked, we also split this data or the cells into two parts. So when price is less than 135 goes to the left hand side. When price it's above or equals to 135 will goes to the right hand side. And the price when we are giving a class which is the shelf locks, it's good, and the price is greater or equals to 135, the sales of that product will be 7.462. So that's basically the leaf that we get from this particular tree models. And on the left hand side, when the price actually below 135, as you can see, well, it's split again. When United States, the variable will say no, right? It's not from the US. It goes to the left hand side, which give you the leaf 9.45. And when it is in the United States, the leaves actually give us the projections here, which is 11.77. So that's basically describe all the classes on the goods category here. Well, when shelf locked, it's actually a bad and medium category. You also want to look at this side right here, the left hand side, and then it divides up the price into less than 49.5 and anything greater or equals to 94.5. And then it keeps splitting up, and as you can see, well, how many total knots we have. So this is one knot in terminal knots in our tree, and this is the second one, this is the third one, fourth one, fifth one, fifth ones, sixth one, seven ones, eighth, 9, 10, 11, 12, 13. So total it should add up to 18. So we should have total of 18 terminal knots in this case. So that's why using visualizations for the tree models, it's going to give you a very good interpretations to explain for your results. Now at this point, not only we want to plane out this tree models to see it, we also want to make a predictions of it. So let's use the predictions functions. So predict. We're going to use the tree model. We just save it right from our previous lines of codes. And this time we want to actually put in the testing data. We put in the testing data into our trained models and trying to make a predictions of cells. And we're going to save this to tree predict. Well, in this predictions, you can see what is being saved. So if you print the names, right, of the tree predictions, you are going to see all the predictions, right, from each observations in your testing sets, right? So it will give you it will return 400 of predictions. So as you can see, well, the name of each predictions, it's given a number here, right? So you want to actually see, well, what's stored in, let's say, well, prediction 1. Right, so maybe you can print it out here. So the first one right here, oopsie. So let's see. So let's see, 1, not an 8. Okay. So in this predictions, we get 2, and let's see. Oh, okay. So I see. So we can try to print the tree predictions. Let's say I want to know the first ones, right? So what is the values that we predict using the first rows in the testing data sets? Let's see. Oh, not quotations, just one right here. Yes. So using the first rows in your testing data sets, the cells from the models, from the trained model, we predict the value of the of the cells will be 11.77091. So that's basically how we can use the prediction functions by passing in the testing data sets and make a predictions of the cells. And now what happened is we want to calculate the errors for this testing data sets, right? So how well the model actually predicts the results from the unknown testing data sets. So we're going to use the predictions minus the actual outcomes in your testing data sets, which is the cells columns in your testing data sets. And you get a difference of the two, and then you square it. Again, well, this is the process to create the mean square error. So let's print this. So as you can see, well, the results returns, the mean square error in this case is 4.922039. Well, again, well, by using a tree model, we are actually building a tree structure here that minimizes the mean square error for the training data sets. And this testing data sets giving us an idea how well the model actually predicts the unknowns new data. Well, we want to also note if this is the result we get from a basic tree model, can we actually print our tree? By printing the tree, we are basically trimming the tree to get a better result. So let's go into this pruning process here. So in order to actually print a tree, or maybe to trim a tree to make a better result, the whole idea is basically to reduce the case of overfitting. Right? So pruning tree has an objective. The objective is to reduce the level of overfitting. So maybe we can do better by pruning here. So again, you can actually setting your random seeds again by because later we are going to see how we're gonna use our randomings cross-validations process here. So let's say we're using the same random seed here, and this time what we want to do first is to use the cross-validations. Again, well, we learned it from the last chapter. The main purpose for cross-validation is to basically getting a general result of a validated mean square error, right, from the models. And this time what we want to do is to use the cross-validation process to find out what size of the tree will have or will provide the lowest mean square error. So in another word, we want to actually use this function cv.tree to kind of check the size of the tree related to its error rate. So let's use a cross-validation model with the degree of 5 here. So again, degree of 5 means we want to actually chunk up this total data set, which is 400. Actually not 400 because we only have 200s in our training sets. So we want to actually chunk up this data that we trained and into 5 different degrees, which is corresponding to the alpha terms, so that we can look at how well it predicts the results again. So let's use the cv.tree models and put in the model that we trained before, the tree model, and k is equal to 5, so we're going to use 5-folds cross-validations. So we save it to cv_tree. And if you want to actually see what it is, you can print the name of the saved tree model here. So you want to actually look at, well, what it's being stored. So there are 4 things being stored: the size of the tree, the diff of the tree, which it's referred to the cross-validations error, and then we have the k, which corresponding to the cost complexity parameters that we discussed in the book, which is the alpha term. And then we have methods. So again, if you want to actually see what it is, you can basically just call this out and you can see those numbers. So cv_tree. So as you can see, we are printing out the size, which is the size of the tree. Again, the size of the tree referred to if the tree has only 1 terminal knot, 2 terminal knots, 3 terminal knots, 4, 5, 6, 7, 8, and then later it's split in a different size, right? So we have 8 jump to 10, 11, 12, 13, right? 18 is the maximum knots in our models. And for each size, we have the error terms. So as you can see, we have the error term for the tree that has 1 terminal knot, tree that has 2 terminal knots, and then so on. The last one right here will be the tree with 18 terminal knots. And k here represents the cost complexity parameters. Right? So basically we have the alpha defined here, and methods using a deviance, and we also have the pruned parameters here defined. All right, so at this point, we still cannot see very clearly when is the tree going to do the best. So by looking at this result here, we only can see that in the trainings, in the training settings, right, with the training data, when we have only 1 terminal knots, we have the highest error. And the training data also suggests when we have a 18 terminal knots, we have the lowest error, and which is of course true, because well, the more complex the model is, with the training sets, the lowest the error should be. However, again, the whole purpose for using a pruning method is to reduce the chances of overfitting. So we don't want to trust this result here, because well, when we have a slightly different data sets to put into our trained models, we might be misclassifying the the new data. So that's why we want to actually add this parameter here. Right? Remember the cost complexity parameter. When we have total of 18 terminal knots used, we are going to have a very, very extremely low, which is negative infinities of the time complexity. However, as we move to a upper tree, right, when we start trimming our data, we should actually see our complexity parameter to start going up to compensate. Right, so when we actually reduce some of the terminal knots here, the cost complexity should be compensating. All right, so again, well, how do we know which one is the best? Well, we are going to use the plots to basically plot out the size of the tree and also the error terms. And we would like to see how well the tree will behave with different level of sizes. So let's plot this. So, okay, so I haven't run some random seed here yet. So random seeds. So we're gonna load this again. And we are going to have this. Okay. So we have size of the tree right here. So again, it depends on how your randomized seed is being set, because it has something to do with the cross-validation process here. Right, so the randomness is going to pass into this 5 sections. Right, so how the test is being sectioned out. So in this case, we have the lowest error here that is stating at around size of 9. So we have a cross validations that giving us the answer here, where the error terms will be the lowest when we reach to this not equals to 9. So maybe the size is equal to 9 in this particular case. Now we want to actually trim our tree based on the cross-validation results. Right? So we find how many terminal knots we should have in order to reduce the overfitting problems. We are going to use a tree model, which is pruned.tree, and trying to trim the full tree. Right? So again, the tree model that we came up in the last exercise basically give us the full-grown tree. We want to trim it. We want to actually reduce the total number of terminal knots. And we are going to specify here using best equals to 10. We only want, actually in this case, we want only 9 of them from our cross validations. Right? So we only want 9. And we're going to only have 9 terminal knots in this case. So let's save this. And we're going to plot the tree again. So as you can see, it's much simpler tree structure here. And we're going to put the text in there. And now, well, the final step here, of course, is to basically give us an idea how well it predicts the testing data. So again, we follow the same thing. We use the predict functions, but this time we're not using the tree model, but we're using the pruned tree models. And then we pass in the testing data sets to make a predictions. And now the final steps is to calculate the mean square error. So here goes. So we use the predictions from our printed model and the testing outcomes, which is the cells in the testing data sets, and square the terms. So as you can see here, we are getting a result 4.918134. So comparing to our previous, let's say here. So obviously, when we have a simpler models here, right, we trimmed the tree to be a much simpler structure. We only have 9. total of terminal nodes, which is only half of the original growing tree, we can actually improve our predictions. We reduce our mean square error by close to 0.004, which is better results. So that means this trimmed tree not only give us a good predictions with the training data sets, but it can actually better to predict the new unseen data sets. So this is basically an exercise for you to start realizing, well, when you're building a tree models, you do not want to just build the basic tree model and say, hey, that's the best you can do. Building a tree model using a tree functions here will only return you with the full growing tree, the full size of the tree. However, you always want to test it to see if the full size of the tree is a better model to use when it faces an unknown data sets. So if you are able to print the tree and reduce the number of terminal nodes in your model to make it a simpler model to reduce the chance of overfitting, you should always try. You should always try to use the cross-validations methods to find out whether a full growing tree is better, or should you actually use a different size of the tree for your predictions. So hopefully you'll enjoy this video. Again, the tree model is one of the most basic statistical tool that we use for making a business decisions. So I'm hoping that you are now getting a better idea about how to build a basic tree models with this exercise. So next time we are going to come back and start on a new topic, which is fitting a regression trees and doing some testings. Alright, so I will see you in the next videos.